Okay, welcome back. It's our second video lecture in endocrinology. We're going on to a new topic now, which is regulation of metabolism. Um, Metabolism is going to fall into two categories, maybe 2 or 3 lectures. I'm not sure yet. The first lecture is going to be the things that happen in the gut, and the second lecture will be on the endocrine pancreas, because there's just so much going on with the pancreas, with particularly insulin and then diabetes. So that may take 2 or 3 lectures. I mean, 1 or 2 lectures, and we'll have 1 lecture just on the gut today. I hope you're able to keep up. I've pretty much decided that the final exam will be a multiple choice exam with based on all the material that we covered since the last exam, and probably represented about 150 points instead of 200. I think it's probably unfair to have so many points under the circumstances, and probably your final grades are getting up a little better, or maybe where you are right now, but I would be shocked if anybody's grade goes down, especially with a 50-point writing assignment coming in. I might have some more writing assignments coming, so those usually give you most of the points. Anyway, this I believe is chapter 6, and let's just get started. If I can get my PowerPoint to be on the same page with me. So regulation of metabolism, the background for this is that ingestion and utilization of nutrients are needed to provide cells and tissues with everything they need for energy generation and anabolic process of building your body. This is homeostasis. This is endocrine regulation of everything you need, the nutrients that you need to keep the cells happy. It's a complex activity that involves physiological systems responsible for food ingestion, digestion, absorption, distribution, and then utilization of nutrients. And storage is in there too. These activities are under complex endocrine control, that's why it's in this course, involving the interaction of hormones, including and paracrines and autocrines, from the gastrointestinal tract, the endocrine pancreas, the adrenal cortex, and the thyroid gland. Now, we've already talked about the thyroid gland, and a few lectures from now we'll talk about the adrenal cortex. So the next couple lectures are going to be on the gastrointestinal tract and the endocrine pancreas. The so-called gastroenteropancreatic hormones are responsible for the following functions, but let me break that down. Gastro, stomach; entero, gut; pancreatic, pancreas. So you can pretty much figure out what we're talking about for that. They're responsible for regulating, coordinating the functions of the GI tract, the appropriate distribution of all the products of digestion, and the maintenance of appropriate levels of circulating metabolites essential for metabolic activity. Glucose being the number one, but there's other things that you have to, amino acids and other fats that you have to circulate as well. The gastroenteropancreatic cells that are going to secrete the various hormones, paracrines and autocrines that are involved in digestion have certain characteristics. The GEP cells are all protein hormones. There's no steroids. There's no amino acid derivatives. They're all peptides or proteins. They act at every level, as I've indicated: endocrine, paracrine, and autocrine, and they're distributed in different manners. They can be distributed as single cells scattered throughout a tissue. So, for example, the cells that make secretin are in the duodenal, the duodenum, and the mucosal layer of the duodenum. They're just kind of scattered throughout. They can be aggregated in discrete masses with some kind of organization. This is true of the pancreatic islets with the alpha cells, the beta cells, the somatostatin cells, organized into these what we call islets of Langerhans, which is separate from the exocrine part of the pancreas. Or they can be found in close association with other GEP cells, but a real low concentration. So somatostatin cells, which are inhibitory on almost every digestive function, can be found with nearby gastrin cells in the antrum mucosa, the mucosal cells of the antrum of the stomach. GEP cells are typically protein secretory cells, obviously, because these are protein hormones and protein signals. They have, like all protein secretory cells, a lot of extensive rough endoplasmic reticulum, because you need that to make them, prominent Golgi to package them, and a lot of secretory granules, which are waiting for secretion. GEP cells have been characterized in two ways: open or closed type paraneurons. The reason they're called that is because these GEP cells are often found near neurons, because they're either receiving signals from the neurons or they're sending signals to the neurons. The open type paraneuron is an epithelial cell, so it's right lining the lumen of some structure, usually the gut, that has one pole in contact with the lumen or cavity of an organ, for example, the lumen of the gut, and the other pole in close proximity to the vasculature of the bloodstream, but also in close proximity to neurons as well. They receive their stimuli directly from the lumen, so they're cueing on what's in the lumen, amino acids, glucose, anything like that. They secrete their signals in the extracellular fluid near the bloodstream, or nope, I have to stop for a second if I know how. Wow. Oh well, we're just gonna deal with it. Stop it. I've got dogs, I've got children, I've got all kinds of things, but I'm going to keep this going because once I get started, I hate to stop. I apologize for that. My daughter will probably be up in a second, but you'll get to meet my daughter. So open type paraneurons are lining the lumen of the gut. They're going to be measuring the gut, looking at the contents, and they're going to be talking to either the bloodstream or they're going to be talking to nerve cells. Examples are gastrin, secretin, and cholecystokinin cells. Those are classic open-type paraneurons. Closed-type paraneurons are located outside the epithelium. They're distant, and they're not in contact with the lumen. They're getting their signals from the bloodstream, not from the lumen of the gut. They receive stimulus indirectly, and they secrete product in the extracellular space near the blood. The best example of these are a lot of somatostatin cells are distant. Some of them are nearby, but none of them are right in the epithelium. But the pancreatic endocrine cells in the islets of Langerhans are classic examples. Pancreas is not in contact with the gut. It gets its information from the blood, mainly measuring blood glucose levels. All right, here is a picture showing GEP cells in an open-type paraneuron situation. The arrows are pointing to the stimulus, which could be glucose, it could be amino acids, it could be fatty acids. Whatever's in the gut can be a signal. This is the lumen of the gut that we're looking at there where the arrows are. There's a couple of cells that are labeled endocrine, but they could be actually endocrine, paracrine, or autocrine. And then down below you can see that they're in contact with a number of different things. They can be right near a capillary where they're going to dump a signal in the blood. They could be connective tissue cells that they're signaling. There could be arterioles that are there that they're signaling. That would be for vasoconstriction or vasodilation, not to put the signal in the blood. You can only put a signal in the blood in a capillary. You can't put it in the blood in an arteriole because there's muscle layers that prevent that. So when they send a signal to an arteriole, that's for vasodilation or vasoconstriction. Smooth muscle, that would be for smooth muscle contraction, moving things through the gut or inhibiting movement through the gut. And nerve fibers, that can be telling the nervous system what's going on. So open-type paraneurons are one of the two. The other ones are the closed type, and that's, like I said, the islets of Langerhans and the pancreas would be a good example. GEP hormones can be categorized according to relatedness of molecular structure. There's several families of GEP hormones. Remember, a family of hormones are just things that are related through evolution. There was originally one signaling hormone. There might have been a gene duplication, or there might have been a whole genome duplication. Now you've got two copies of that gene. One of them is free to vary, and that's end up creating hormone families. So gastrin and cholecystokinin are one family, the gastrin family. There's also a cholecystin-like peptide and a skin peptide called cerulin. Excuse me. I do not have the virus, but I was just outside, and I think I picked up some pollen or something. All of these, the two that are most important for what we're going to do is gastrin and cholecystokinin. All these have 5 identical amino acids at their carboxy terminals, and they have a conserved tyrosine, either 1 or 2 residues next to that. The 5 C-terminal amino acids are sufficient for activity of most of these hormones, strangely enough. The tyrosine may or may not be necessary. A pharmaceutical drug has been made called pentagastrin that is just those 5 amino acids. It's used for both medicine and for diagnostic purposes. The rest of the molecule, because it can be a very large molecule for these signaling molecules, can help with potency, to regulate target specificity, which hormone, which receptor does it bind to, things like that. Now, gastrin and cholecystokinin are sulfated on that tyrosine residue, which is necessary for CCK activity, cholecystokinin. But the sulfate is often replaced with a phosphate group in gastrin, and it makes it more active. So it gets that tyrosine gets phosphorylated in gastrin, but it sticks with the sulfate group in cholecystokinin. Gastrin and cholecystokinin both have multiple molecular forms. Gastrin has at least 3, which I'll show you in a minute in a picture. Gastrin 34, gastrin 17, and gastrin 14. Cholecystokinin has at least as many forms. The various forms probably bind to the receptors with different affinities, or they bind to different receptors. There's also a secretin family. It includes glucagon, which is going to be very important when we talk about insulin regulation, because glucagon is an anti-insulin hormone. Secretin, vasoactive intestinal peptide, gastric inhibitory polypeptide, those are all GEP signals. Glucagon's coming from the pancreas. The other ones are coming from the gut itself. Also included in this family are some things that are known mainly for the nervous system, but also turned out to occur in the gut. VIP, PHI, PHM. We're not going to worry about them too much. The point I want to make here is that the gut signaling pathways have probably been around forever. I mean, face it, digestion had to come very early in animal development. And a lot of these turn out to also be brain polypeptides. So it's likely that before there was cephalization and development of the brain, you still had to digest them. So that the nervous system was probably centered around the gut, and later brain development occurred, and it usurped a lot of the signals that were going on in the gut. So I think that's why when you look at the gut and you look at the brain, you find a lot of the same things. Now, my wife has always said that my brain is being driven by my gut, but I don't know what she's talking about. Primary structures are gastrin and cholecystokinin. This is gastrin 17, one of the shorter ones. There's up to 30 amino acids, 34 amino acids on gastrin. N-terminus has a pyroglutamate. The C-terminus has an amine group added, so that's why it should say COOH, but instead it's CONH2. Kind of unusual to have an amine group at your carboxy terminus. But notice the tyrosine that's right upstream of that 5 conserved amino acids that are there, gly, trip, met, asp, phi, is sulfated. That sulfate group is important for cholecystokinin function. Notice that its conserved tyrosine is moved over by 1 amino acid from the 5 conserved ones. In gastrin, that sulfate group may be replaced by a phosphate group, and that seems to bind the receptor better. In cholecystokinin, that sulfate group seems to be important for cholecystokinin function. Okay. Here's just an example of the isoforms. We got, I love this, big gastrin, which I also call pre-progastrin, 95 amino acids. That's what gets secreted. Gastrin, big gastrin, is 34 amino acids, has pyroglutamate. You can see the 5 conserved amino acids along with that sulfated tyrosine. Gastrin 17 is little gastrin, has pyroglutamate. The N-terminus has the 5 conserved amino acids, and then the tyrosine with its sulfated. And then mini gastrin, gastrin 14, is cut off. All of these are effective in different tissues, but they probably either bind to different receptors or they have different affinities for those receptors. So there's a lot of regulation going on here. Pentagastrin is a drug that was produced by the pharmaceutical companies that has just those 5 amino acids. It mimics endogenous gastrin, so it acts like gastrin if you give it externally. And it stimulates gastric acid secretion, so it stimulates pepsinogen secretion, and it's identical to the 5-carboxyterminal amino acids of gastrin. So and it's also used diagnostically. If they think there's something wrong with your gastrin secretion system, with your ability to produce stomach acids in general. People have digestive disorders. They can give you this compound and find out whether you produce stomach acid. So is it a signaling problem? That other family I talked about, secretin, has a vasoactive intestinal peptide, secretin, glucagon, and gastrin inhibitory peptide. Notice there's a lot of homology between these different peptides. So that's why it's a family of these. Secretin will be a little, we'll talk about it a little bit in today's lecture. Glucagon is going to be really big in the insulin story. Insulin, pancreatic polypeptide, and other families also occur. The insulin family is composed of 2 polypeptide chains that are linked by disulfide bonds, but the 2 chains are synthesized linearly as a single polypeptide, and it has a connecting peptide in between them. They fold over, they form some disulfide bonds. There's an internal disulfide bond also within one of the chains. And then the C peptide gets cleaved out, and you're left with insulin. And this is produced by the pancreatic beta cells. We're going to spend a lot of time on insulin later, so I'm just mentioning it now. Nerve growth factor is also related to insulin. It comes from the nervous system, and it's similar to insulin-like growth factor, which we knew as somatomedin, also from the liver under growth hormone regulation. They're in the insulin family. So they're all kind of related to each other, and they all bind to those growth factor type receptors. Pancreatic polypeptide is a family. It's produced by the pancreas, by the PP cells in the islets Langerhans. There's 2 other peptides in this family, PYY from the intestine and NPY from the brain. So there's another one of those gut-brain connections that I was talking about. Substance P and bombesin and related peptides share a common C-terminal, so they must be from an ancient family. Bombesin was described from amphibian skin, but it's now known from the mammalian gut and lung tissue, and what we're going to see that is actually gastro-releasing peptide. So the bombesin-like peptide that we find in the mammalian small intestine that we call gastrin-releasing peptide, based on its action, which is to release gastrin. Somatostatin and metilin don't appear to belong to any family. Somatostatin is going to be inhibitory in every function associated with the gut, just like it was inhibitory on growth hormone release from the. It was the inhibitory hormone for the hypothalamus that inhibited release of. From the anterior pituitary inhibitors of the growth hormone. I had it right the first time. Motilin doesn't appear. Motilin's going to make the gut move. There are other GAP hormones, substance P, which is also known from the brain. Somatostatin is there, motilin, neurotensin. These are all players. We won't go into much detail on these other than somatostatin. Before we can get on regulation, we have to look at the overview of the gastrointestinal tract. The GI tract runs from the stomach to the rectum. Obviously, before that, you have the mouth and the esophagus. We're not including that in the GI tract, but it is included in what we call the gut or digestive system. In order, or the GI tract is divided into stomach, where we're going to start small intestine, which is separated from the stomach by a sphincter, the pyloric sphincter, which can open and close to let things into the next level. The first part of the small intestine is duodenum, then the jejunum and the ileum, and then you get to the large intestine, which starts as a colon and terminates in a section called the rectum. At the junction of the small intestine and large intestine is a little side pouch called a cecum, and the cecum has an extension on it called the appendix. Small intestine in man is about 20 feet long. Large intestine is about 5 feet long. Consists of the cecum with the appendix on top of that, the colon, and then the rectum. Each region has a specific function. We're going to focus mainly on the stomach and small intestine for our regulation today. Large intestine is, some functions are controlled by the nervous system, but many functions are controlled by endocrine, paracrine, and autocrine signals. The GI system is extremely diffuse with the distribution of hormonal cells. You never know where you're going to find a GEP cell. So endocrine cells are distributed in the mucosal epithelium along the length of the entire tract, but also in accessory organs like the pancreas. The stomach has mainly gastrin cells as GEP cells. Sabrina, I'm in the middle of a lecture, so can you not talk to me?
I'm not talking to you.
Okay, good. Don't.
Talking to my brother.
All right. You guys want to talk to my daughter, you can, but I don't want to talk to her. All right. We got everybody here. Now the dogs will start barking. All right. Small intestine has cells that secrete secretin, gastrin, cholecystokinin, methyllin, gastrointestinal inhibitory peptide, enteroglucagon, and many others. If you guys can make any more noise, that'd be great. Enteric neurons producing vasointestinal inhibitory peptide, substance P, and enkephalin, bombesin are found throughout the tract. So there's neurons that are producing neurotransmitters, and then there's things that are producing endocrines, autocrines, and paracrines. Somatostatin cells are found diffusely through the entire tract. Just remember, somatostatin is always inhibitory. Everywhere you find it, it's inhibitory. So let's go into the general actions. Gastrin is secreted by cells in the antrum of the stomach. That's the upper part of the stomach, and in the curve a little bit, mainly, but the upper part. The upper small intestine also produces gastrin. Gastrin is a hormone, or it's not being dumped into the gut. It's being dumped onto things that can affect the gut. So the principal function of gastrin is stimulation of acid secretion, which is protons, by the parietal cells of the stomach. So gastrin is being produced by the stomach and small intestine to cause these parietal cells to produce acid. It also promotes pepsinogen release by chief cells. So parietal cells make acid, chief cells make pepsinogen. Pepsinogen is cleaved into pepsin by the acid. So pepsin then goes on as an enzyme to break down proteins and peptides into smaller pieces in amino acids in the stomach. So you start digestion, with basically bicarbonate amylase in your mouth and chewing. It goes down to the stomach, so it's pretty crude. It's just a little bit chewed up, and it's some of the starch degraded by amylase, but all the proteins are still intact, and everything else is still intact. But you start on the proteins right away in the stomach, and that's gastrin's job. Acid and pepsinogen cleave to pepsin, and that gets you to digest these proteins and peptides into smaller pieces of amino acids. They then get passed on into the small intestine. Acid secretion is associated with presence of food in the stomach and is stimulated by three things that act synergistically. Acetylcholine from neurons. Well, how do the neurons know that you want to secrete gastrin? That's all that mental stuff that says, I'm about to eat, I'm now eating. This is the knowledge that food is coming in from the brain. So the brain's telling your stomach, get ready, start making some stuff because we're going to have a bunch coming down the pike. And that's what acetylcholine is coming from neurons, typically parasympathetic input from the vagus nerve. Histamine from the stomach. There are cells in the stomach that produce histamine, and histamine is going to be involved in acid secretion. And then gastrin from the antral and small intestinal duodenal cells. The three together are going to act synergistically to create your acid that goes in the stomach. Gastrin secretion itself is stimulated by distension of the stomach, so you actually have to feel the stomach has to be stretched a little bit. Presence of peptides and amino acids in the duodenum, that was because there's a positive feedback. A little bit of acid and pepsin breaks up the proteins and amino acids. Once those get moved into the gut says, oh, let's make more gastrin. And then vagus nerve discharge later on of gastrin releasing peptide. So the vagus is contributing the acetylcholine to some extent and the GRP to get the gastrin. Gastrin secretion is inhibited by negative feedback by acid in the tract through negative feedback mainly at the gut in the small intestine. So if a ton of acid gets in the small intestine, it shuts down gastrin. And by secretin, cholecystokinin gastric inhibitory peptide, glucagon, and VIP. So once you get a whole bunch of these duodenum enzymes all cranked up, hormones and endocrines, and autocrines. Once those are all cranked up, they all inhibit gastrin, because you're probably already there. They're all caused by food that gets into the small intestine. So if you have a whole bolus of food in the small intestine, they say, hey, let's slow the stomach down, and they have negative feedback on gastrin. Secretin is produced by cells in the small intestine, particularly duodenum and jejunum. Secretin promotes the release of electrolytes, mainly bicarbonate, and water from the exocrine cells of the pancreas. So secretin is going to produce bicarbonate, which is going to neutralize that acid in the small intestine. The end of the stomach only has one enzyme acting in it, and that's pepsin. And pepsin loves an acid environment, but the gut doesn't. The gut has all kinds of fat-dissolving compounds, protein-dissolving compounds, DNA-dissolving compounds, and they don't like that at low pH. They want to be, more neutral pH. So secretin's going to do that. It's going to get the exocrine part of the pancreas to make water and bicarbonate and dump that into the small intestine. The stimulus for secretin secretion is the acid levels. So high acid also gets secretin to be dumped in. That dumps in bicarbonate to lower the acid. But biosalts coming from the liver are also, at least liver or the gallbladder, depending on whether you use the direct route or the indirect route, they're going to also stimulate secretin. Somatostatin and metencaphalin are inhibitors. So everywhere you go, somatostatin is going to be an inhibitor. Cholecystokinin, CCK, is secreted by cells in the small intestine. The principal function of cholecystokinin is to get all the digestive stuff done, breakdown of food, stimulation or release of the pancreatic enzymes in the small intestine. The exocrine part of the pancreas creates these zymogens. The zymogens get into the lumen of the small intestine and get activated, and they break down peptides, and they break down fats, and they break down everything else that's in the gut, so they can be absorbed as nutrients into the body. Also, CCK, which is what the name implies, cholecysto means gallbladder, kinin means movement. So cholecystokinin causes contraction of the gallbladder, which releases bile in the small intestine. Bile is made by the liver, but it's there for breaking up fats. So cholecystokinin is dependent on the presence of proteins, peptides, and amino acids in the duodenum. Once those nutrients start showing up in the duodenum, cholecystokinin, you make sure that the pancreas delivers the right materials to break them down. Amino acid leucine and phenylalanine are especially potent secretagogues. I know I'm coughing in my hand. I'm supposed to cough in my elbow, but I don't have any interaction with anybody. As you saw, I didn't even interact with my children. So I'm going to cough into my hand during the lecture. Free fatty acids are also potent at causing CCK. So leucine and phenylalanine means that you're in the stomach, you've broken down a bunch of amino acids, proteins, peptides into amino acids, and these two amino acids are going to cause CCK release. But free fatty acids, which are also going to be freed up by the churning of the stomach, they're going to cause CCK release. Motilin, secreted by cells in the mucosa of the stomach and small intestine, it stimulates gastric and small intestinal motility. So it gets the stomach churning and it gets the small intestine moving, so you can move the food along. There's neural input to the stomach as well. The gut. The gut, the waves peristaltic waves that move food down the gut have a lot of neural input from the nervous system. It's inhibited by somatostatin. That's not a real stretch. Gastric inhibitory polypeptide, just what it says. It's going to inhibit gastrin release. Synthesized and released by cells from the jejunum. The GIP functions are inhibit acid release from the stomach, stimulate insulin release from the pancreas. So this is going to be big when we get to the pancreas. GIP release is stimulated by glucose in the GI tract. So it's measuring glucose, and it causes this, and then fat in the GI tract. So these are all coming from the stomach, and it says, okay, let's slow things down. Somatostatin is the main inhibitor of GIP. So somatostatin just inhibits everything. Then a couple more gut hormones that we're not going to focus much on, but I just thought you should know they exist. Interglucagon is produced by cells of the ileum and the colon, way down at the end of the small intestine and the beginning of the large intestine. The main function is to stimulate growth of intestinal mucosa. Digestion is pretty rough, and a lot of cells are sloughed off. It's like your skin. You got to keep replacing those. You need an interglucagon to keep replacing that intestinal mucosa to keep those cells there. Interglucagon is stimulated by the presence of food in the intestine, so just anything moving through will keep it going. Glucose and triglycerides in the meal are most important stimulators. It's also, strangely enough, elevated during pregnancy. Neurotensin secreted by the small intestine. Principal function is to inhibit gastric motility. Primary stimulus is fat in the small intestine. So just another thing that says, once you get enough stuff in the gut, you kind of want to shut the stomach down for a little while. So there's a back and forth there. Bombesin, which is really gastric releasing peptide in mammals, is produced by cells in the stomach, small intestine. Its function appears to be stimulation of gastrin from the cells of the stomach. So this is one of the major causes for release of gastrin. It's stimulated by acidified food. So you eat a meal, it goes to your stomach starts churning, stomach produces acid, it produces pepsinogen, which gets cleaved to pepsin, and then your pyloric sphincter periodically opens and closes. It opens, it sends some food in the small intestine. That food's picked up, acidified food is picked up by the bombesin cells. They see that and they release bombesin, gastric releasing peptide, and that causes you to release more gastrin. So it's kind of a positive feedback early in digestion, negative feedback later in digestion. Somatostatin is produced in all areas of the GI tract. Its effects are inhibition of secretion of nearby hormones, paracrines and autocrines, and inhibition of contraction of nearby smooth muscles. Somatostatin is just inhibitory across the board. And then VIP, vasoactive intestinal peptide, substance P, and keflin are neurotransmitters that are produced throughout the GI tract by the nervous system, and they're involved in regulation of smooth muscle contraction and secretion of certain hormones. All right, I lost where I was. Okay. Vasointestinal is a multifunctional neuropeptide with roles way beyond, all through the body. This is where the gut and the brain intersect through, very early, evolutionary early substances that are present in both the brain and the gut. All right, let's talk just for a minute. We're not going to go into this in great detail, but just for a minute on how do you regulate stomach acid and pepsin in the stomach. First, your brain knows that you're eating. It even knows when you're thinking about eating. And so there's higher brain centers that are going to control. And then there's the distension of the stomach when you actually start eating. Those two things, the higher brain centers telling you that you're eating, and then the distension of the stomach go to act on the G cells that are located in the upper antrum of the stomach. And the G cells are going to produce gastrin. The gastrin is going to inhibit activate parietal cells and cause them to make hydrochloric acid. The hydrochloric acid or gastrin are a combination of the two, stimulate chief cells to produce pepsinogen. The acid cleaves the pepsinogen into pepsin, and the pepsin goes to break down proteins, peptides, and amino acids. The peptides and amino acids early on have a positive feedback on the gastrin cells, causing them to make more. But at higher levels, they have negatives. There's also negative feedback situations. Hydrochloric acid, not hydrochloric acid, but it really shouldn't be HCl. It should be H+. But anyway, the acid has a negative feedback on the G cells, causing them to stop gastrin. So once your stomach has a ton of acid in it, it's supposed to stop producing gastrin so you don't make more acid. There's also negative feedback from vasoactive intestinal peptide, the gastrointestinal peptide, inhibitory peptide, somatostatin, and even a hormone called bulbogastrone, which I didn't mention. These are all negative feedback on the G cells. So once the stomach has enough acid, it tries to shut it off. As you know, this doesn't always work, though, does it? So if you look down below, there's supposed to be neutralization of this stomach acid once you get into the gut. So if you see that you have a whole bunch of acid coming from the fundic, meaning stomach, mucosal layer, producing a bunch of acid. That gets, once you go through pyloric sphincter, it goes to the duodenal mucosa, and that duodenal mucosa has secretin cells in it. The secretin cells secrete secretin, goes to the pancreas, and the pancreas knows it needs to make bicarbonate, and the bicarbonate starts to neutralize that stomach acid. So you're supposed to be at very low pH in the stomach and close to neutral pH in the small intestine as a result of secretin. Now, regulation of stomach acid is huge. I mean, we're talking about blockbuster drugs. Antacids are blockbuster drugs. So for the longest time, our antacids were bicarbonate. You would just mix some bicarbonate and water, and that would be an antacid. And then they finally figured out that histamine secretion had a role in that, and they started making histamine blockers. So things like Benadryl and Tagamet was the big one, histamine blocker that was supposed to help you with stomach acid secretion. And then they came up with the idea that why don't we just block it at the parietal cells? And they came up with proton pump inhibitors, which all of the antacids that you take now are proton pump inhibitors, and that would be Nexium and Prilosec and those things. There's a whole series of them, and so the history of pharmacology on this has gone from blocking the acid itself with antacids to blocking the histamine production to blocking the actual production of the protons themselves. But look at this pathway. There's the luminal amino acids. When amino acids reach that, they have a positive feedback on the gastrin cells. But also there's inhibitory, there's things in the brain that tell you to produce gastrin. So the gastrin cells located in the stomach and also in the upper small intestine produce gastrin, which acts on these interchromaffin-like cells, ECL cells, to produce histamine, and that acts on the parietal cells to stimulate acid production. But the vagus nerve is also producing acetylcholine that acts on the parietal cells to increase acid production. So you have several things working together. Acetylcholine, histamine, and gastrin are all stimulatory for proton release, and any two of the three is a better effect, so they're synergistic. Histamine alone causes some activity, gastrin alone causes some activity, acetylcholine alone, but you put any two together and you get a lot more. Put all three together and you get a lot more. So that's why the histamine blockers like Tagamet are only partially effective at blocking acid secretion in people who had acid reflux disease. Right now they're focusing, instead of on the regulation of the parietal cells, just block proton production at the parietal cells. So you can see it's pretty complex. Gastrin itself has negative feedback on gastrin once it gets high enough. Acid has negative feedback on gastrin. Somatostatin has negative feedback not only on gastrin but on parietal cells. So it's pretty complex regulation of acid. But right now the modern pharmacology is focusing on the parietal cell with Prilosec and Nexium. Nexium is a pure isomic. There's an L and there's two directions, the left and right facing molecules, and Nexium is a pure product that faces the correct direction, and whereas Prilosec, half of it faces the right direction and half of it doesn't. More than you wanted to know. Bottom line is Nexium is better than Prilosec. There's also synergy on the pancreatic enzymes. Cholecystokinin binds to a receptor and stimulates an IP3 pathway. But on those same cells, there's also secretin receptors that work through a cyclic AMP pathway. If cholecystokinin binds to the center cells of the pancreas, you will get some enzyme secretion to break down fats, to break down proteins, to break down nucleic acids. But it's kind of low. But if you add cholecystokinin on its receptor and secretin on its receptor at the same time, you see the arrow is much bigger and you get a lot more enzyme secretion. Similarly for bicarbonate, if you put secretin alone, it binds to its receptor. Cyclic AMP will increase bicarbonate secretion, and you'll start to neutralize that acid in the small intestine. But if cholecystokinin and secretin working together, you get a lot more bicarbonate. So the bottom line is your best digestion occurs when cholecystokinin and secretin are both present at the same time. They'll work on the acinar cells, the exocrine pancreas to cause digestive enzymes, the zymogens to be produced, and they'll work on the ductal cells to cause bicarbonate and water production. And so now this one is just kind of, what does it take to digest things? So we got food coming in. That food is detected by the antral cells through a variety of things we've already talked about to produce gastrin. Gastrin goes on the parietal cells to produce gastric acid. Gastrin and gastric acid cause chief cells to produce pepsinogen. Acid cleaves the pepsinogen into pepsin. Pepsin breaks down proteins into peptides and maybe even amino acids. Secretin is stimulated, the S cells, and it acts on the pancreatic ductal cells to produce bicarbonate, and it's synergistic with the pancreatic or seminar cells with CCK to produce enzymes. CCK is produced by the duodenum to act on the pancreatic ductal cells with secretin to help it make bicarbonate, and also the acinar cells to make enzymes. The CCK also stimulates the gallbladder to release bile salts. That breaks fats into fatty acids. Other acinar cells produce zymogens that are converted in the intestine from proteins to amino acids and starch to glucose. So all the stuff that's in your food gets broken down into smaller products. Glucose acts on the duodenal K cells to produce gastrointestinal inhibitory peptide, gastrin inhibitory peptide, which has negative feedback on gastrin, as you can see by the dashed arrow. But GIP also stimulates the pancreatic beta cells to produce insulin because we know there's food there. Insulin's got to work on that glucose. Insulin's going to act on the liver to take glucose uptake. So you can see where the stomach is, where the small intestine is. This is just kind of, wow, here's everything in one diagram. This table right here is mainly for review. It's useful for reviewing the major digestive hormones that I've already talked about. If I didn't cover it, ignore it for exam purposes. But you can see there's a lot going on with gut. When I first started teaching endocrinology, there was not anything on the gut. It just didn't exist. It was like everybody talked about insulin and glucagon, the pancreas, but all these gut peptides nobody talked about. Obviously, they're extremely important. This slide shows you endocrine pathophysiology. So a lot of stuff goes wrong with the gut, and this is listing a bunch of them. The number one absolute gut abnormality in Americans is GERD, gastroenteroflex reflux disease, acid reflux. Acid reflux can be caused by a breakdown in somewhere in the stimulatory pathway for the acid, where you produce more acid than you should, or it can be a failure of the sphincter between the esophagus and the stomach, where you get stomach acid coming up into the esophagus, which it's not supposed to do. So that pyloric sphincter, what is it called? Drawing a blank on it. The sphincter that's at the top, when that sphincter gets, also the esophagus can push down into the stomach, and that causes a lot of issues. So the fact is that millions and millions of Americans suffer from acid stomach and problems related to that. Millions of Americans don't want to be taking antacids all day long like Tums or anything like that. So these Prilosec and Nexium are the drugs of choice now, and they're blockbuster drugs. They're multi-billion-dollar drugs because of that. But that can lead to ulcers. Ulcers are not necessarily caused by acid reflux, but they're definitely related. And then there's some other diseases down here that you can see. The other big gastrointestinal thing that goes on in today's society is either idiopathic, meaning we don't know what causes them, or other diseases where you're either constipated all the time or you have diarrhea all the time. you have pain in your gut and all that. Most of those are autoimmune disorders, and they are not related to what we're talking about here, and they're mainly treated with, now they've started to develop antibody treatments for those various things, Crohn's disease, and any variety of related things. So that's what we have for now. The next one will be on the endocrine, pancreas, diabetes, glucagon, regulation of glucose. I will see you then.